Right, year 12. So, we're looking at the equations of uniform motion. Now we use these to describe five quantities of an object experiencing uniform acceleration. And it's that word uniform that's key here. We can only use these when the acceleration is constant. So that's either, put our physicist hat on, forget about engineering, thinking about a car, we can say it accelerates at 4 meters per second squared for a set length of time. Most often we use these for gravity, because if I drop something, it's going to accelerate at 9.81 meters per second squared constantly. So, 5 factors we're interested in. S stands for displacement, U for initial velocity, V for final velocity, A for acceleration, T for time. They're called the equations of uniform motion or equations of linear accelerated motion. That's all a bit of a mouthful. I call them SUVAT. So to begin with, I'm going to show you where the equations come from and how you can derive them. Now you don't need to derive them. It's interesting, and I think you'll understand them more when you see where they come from. But if you tune out for the next few minutes, that's okay. It's not going to affect your performance in any test. So our first equation is a rearrangement of acceleration. So we know that acceleration is the change in velocity divided by the time taken. Now if we rearrange that equation, we end up with V equals U plus AT. And I think it's a very common sense, easy to understand equation. Number one, because we've got the initial velocity and we're adding the acceleration and how long it's accelerating for. If you start at 20 meters per second and if you have an acceleration at 4 meters per second squared for 4 seconds, well that's going to be 16. So you're going to end up at 36 for our V. So it tells us the final velocity after it's accelerating for a set time. Nice, straightforward. I always refer to this one as VUAT because it looks a bit like VUAT. Our second equation is, again, a rearrangement of something you will already have seen. So our second equation...
Sorry, I knew I switched that light off.
Sorry.
I apologise.
It's okay.
Interrupting.
Not to worry. Do you need anything, or you just hang on?
No, I thought I'd left them on.
Okay, no, that's fine, that's fine.
Checking the
That's
room
okay.
first. I'm sorry.
So, our second equation is a rearrangement of S equals V times T. So S is displacement, V is velocity, and T is time. Now acceleration is uniform, so our average velocity is going to be U plus V over 2. That's going to give us an average velocity. So if we sub this in for V, we end up with S equals U plus V over 2, all multiplied by T, and more commonly, you will see that as S equals a half U plus V, all multiplied by T. And that's our second equation. They're relatively straightforward where they come from. 3 and 4 is when it gets difficult, when we start combining different equations together. So, our third equation, we start where we left off, but we substitute U plus AT into the place of V. So we had S equals a half U plus V all multiplied by T, and we substitute in U plus AT in place of V. So to begin with, that gives us S equals U plus U plus AT all over 2 times by T. Obviously the next thing we want to do is multiply out these U's. So we end up with S equals 2U, 2UT, plus AT squared all over 2. our 2's cancel out, so we end up, our third equation is s equals ut plus a half at squared. This is my favourite of the three for two reasons. I think it looks most physicsy, and this ut factor is lovely. Often you will have s, you will have a, and you want to know t. And you've got a problem if you've got a t and a t squared. They're not multiplied, they're not divided, we can't cancel them down. It gets very, very complicated mathematically. More often than not, you'll apply this equation for something that's starting from rest. So if it starts from rest, u is 0, ut cancels out, you're left with s equals a half at squared. It's a really simple, it's really elegant way it works. Our fourth equation starts off again, we go back to our side, we go back to acceleration. So we said that a is v minus u over t. We've also said that s equals u plus v times t all over 2. And so we start off by saying that, well, a times s must equal v minus u over t multiplied by u plus v times t all over 2. And it looks massively complicated. It is massively complicated, which is why I'm going from my notes earlier. So the first thing we want to do is simplify that down. Our t's cancel out, so we end up with v minus u times u plus v all over 2. Our t's are cancelled out, we've kept the 2. If we expand the brackets out, for a while it gets a bit more complicated, and we end up with v squared minus uv plus uv minus u squared all over 2. Our uv's cancel out, so we end up with as equals v squared minus u squared over 2. And from that point, it's a brief rearrangement to end up with v squared equals u squared plus 2as. And that's our fourth equation. If you lost me, if you didn't understand the derivation, it's not the end of the world. All we have to do is use the equations. I wouldn't be doing my job properly if I didn't show you where they came from. So, we've got our 4 equations. I'll write up so we can remember. So v equals u plus at, s equals a half u plus v times t, s equals ut plus a half at squared, and v squared equals u squared plus 2as. You've got these on the formula sheet. You should know them. You're going to find it very difficult, time-wise, to pick the right equation if you're constantly flicking back, looking for the right equation. You should know these. So if we want to figure something out, there's 3 steps we need to do. First of all, you need to look at what information have you got in a question. Second step, you need to pick which of your equations you're going to use. Third step, you need to rearrange it. Fourth step, we need to put some numbers in. So if I give you a situation of an aircraft, it lands at 40 metres per second and stops in 860 metres of touching the ground. So we want to know how long, what's the time between the wheels touching the ground and the plane coming to a stop. So first thing you should do is write out SUVA. Let's find the information in the question and let's put it in. So it's landing at 40 metres per second. That's our initial velocity. We want to know how long it takes to stop. So if it's stopping, its final velocity is 0. Time is what we want to know. And we know the distance is 860 metres. We don't know the acceleration. So pause the video for a second. Try see if you can pick which equation would we use. Okay, so hopefully you've seen we've got S, you've seen we've got U, you've seen we've got V, you've seen that we've got T. So we've got S equals a half U plus V all multiplied by T. Second step, we need to rearrange that to the form we want it in. So half U plus V times T, so we move the half U plus V over. So we've got S over a half U plus V equals T. No physicist worth their salt should be happy to have a fraction within a fraction. So that half on the bottom becomes 2 on the top. So we've got 2S over U plus V equals T. So we've got 2 times 860 divided by U plus V divided by 40 should equal our time. Now this is the point when you will blindly plug your numbers into a calculator. You will push the wrong sign, you will get the wrong answer. Might not happen today, might not happen in the lesson. At some point, if you just plug all your numbers in, you will get it wrong. You might think you know better, you might think you can do it, you can't. One step at a time. First thing we want to do is 2 times 860. So that gives us, so our top, that's going to be 1720. So we've got 1720 over 40. So as a time, that gives us 43 seconds. What I'd like you to do then, before I see you Monday, is to look at the pages I asked you to read and attempt the summary question from the pages I asked you to read. All you need to do is exactly the same method. Figure out what numbers you've got. Figure out what equation you want to use, rearrange it, plug the numbers in, one step at a time. I'll see you Monday, guys. Thank you.